Hey, good morning, everybody. How's it going? Good morning. Thank you all for joining me this bright and sunny early Sunday or Monday, Tuesday morning. I don't even know what day it is anymore. It's okay. How was the exam from yesterday? How'd you guys feel about it? Probably a loaded question. I don't think I'm gonna get an honest response out of that one from most people. It was terrible. It was fine. That's probably a more honest response. Actually was. Oh no, Molly, that's too bad. He's trying to bark in Morse code the answers for you. It was terrible, but happy with the results. Okay, well, as with most things with me, that's probably how you could best describe it. So that's okay. Hopefully, it challenged your gray matter a little bit to come up with some answers. I think this is where we left off of the introducing models. And of course, if you have questions, chat or this is PowerPoint 7. Finished up. We're talking about linear regressions and all of that, and then we're now bumping into models. In other news, I take call for the Poison Center, so I normally will be on call usually 2 to 3 times a month from 7 p.m. to 7 a.m. So the specialists there at the Poison Center will call me up if they have like a case that warrants it. So like last time it was a couple of snake bites and stuff like that that we're helping to manage. But then I'm supposed to be on call tonight at 7 p.m. But then I get a lovely call at 3:30 in the morning and say, Dr. Wood, you're on call tonight. And I go, oh, you check? It said, well, today's the 29th, right? I go, I don't even know what day it is or month or anything because it's 3:30 in the morning. You just woke me up. And she looks and she goes, oh, I'm so sorry. You can go back to bed. And I said, thank you. I went back to bed. That's fun. Oh, yeah, Matthew. Yeah, it can be not fun to be woken up trying to recombobulate yourself. Sounds smart. Good morning, everyone. Thank you all for joining me again. Bright and early, nothing better than some good old biostats in the morning. Yeah, I agree, Kaylee. Oh, geez. Yeah, that would really stink, Matthew. Oof. Yeah, fortunately, my call is I don't have to go anywhere, so I can just do it, from bed if need be. But yeah. So anyway, so let's go ahead and get started here. I'm gonna start recording. Okay, so we're continuing on with our biostats and epidemiology course here. Checking out the course. We're looking. We have today. We'll have another class session on the 2nd, and then just note here, this is going to be a live session for us. That's going to be our first journal club, and so I'm going to be posting the first article here pretty soon, and then we'll take the first half and go ahead and do the journal club portion of it, and then that's, everyone needs to be there for that because we're also going to be participating, and then the second hour is going to be the review portion of this, so that's going to get you more acclimated to what type of questions we're going to be asking on the exam. So just so you have an idea kind of where we're going, and then you'll have the exam, and then we'll switch gears and move into the epidemiology portion of the course. Some people find that more interesting because they just find the idea of epidemiology more interesting than biostats. It doesn't really matter one way to me. Either ones are totally fine, but you'll see we also have more journal clubs built in, and so I'll give you some more ideas about what that's going to look like later on. So all right, so switching gears here. So we're talking about, we talked about correlation. We talked about how we can use graphs to sort of see how much data covariates with one another. If you take two different variables, whether it's, dose of a medication and blood pressure, or any two variables, so you can correlate them together to see how they covary, right? And remember that if we were looking at an example, say we were going to draw out, a graph here. And then let's see. Imagine we have our graph, and we're going to see, x is the variable we're first concerned with, and then you're going to have your y variable here, and we're going to see how the data sort of lines up. Remember that when you're looking at these, the null hypothesis is always going to be that there's no relationship between the two variables, that the data that you find there is all completely random. So if you were to say look at something that was completely random, it would look just like kind of spots all over the place and nothing really covaried with one another. And if you had a line that would represent that, remember it's just going to be straight across, basically going to be the slope of 0, right? So, but what we can see though, if there is actual covariation in some of the data there, you're going to find there's kind of like a trend to it. So you can see maybe something kind of looking like this, and when you do that, you can get a best fit line, right? So something akin to this. The closer this is to 1 means the slope of the line to 1 means the closer you're going to see that as x increases by 1, y increases by 1, and they covary very tightly together. It may not look like that. Maybe it'll look something more like this, or it could even be negative in some instances if the data actually bore that out. So there's like an inverse relationship between the two, right? So that's just a correlation to see how much the two values actually covary with one another. On the other hand, we talked about a simple linear regression where instead of looking just to see how much do these two factors covary with one another, what we can then do is to see, based on x, what can we predict that y is, right? So we're predicting y from x. So if I change the dose of a medication on the x-axis, how much will that change the blood pressure, right? And so in that case, they remember that when you're just doing a correlation, the two values, it doesn't matter which one's x and which one's y, right? Because we're not doing any predictions. When we're doing a linear regression, it does matter which one is which because we're using y, we're trying to predict what y is based off of x. And based off of that slope, when we get that r squared value, if you recall, you can take that slope of that line and then get the r squared just by taking the slope and getting, multiplying it by itself. And that can tell us a percentage of how much of y that we can predict from x. If it's like 0.13, that means that 13% of y can be figured out from x, right? Because again, if you were to compare like, a dose of a medication versus the blood pressure, we know that the dose is not the only thing that controls your blood pressure. It could be sympathetic nervous system response. It could be caffeine intake. It could be, there's a lot of other variables that are there, right? So when we're switching and talking about models, we want to figure out what those other variables are that are going to be factoring into that. So this is where we're going to getting into models. This is where we're going to talk about multiple regression. Okay. So anyway, so we're talking about models, parameters, and variables here because I don't think we talked about any multiple regressions yet. So we're going to get into that. Okay. So I just want to make sure we're kind of all up on the same page here this early in the morning. So hopefully that makes a sense. So okay, so we're doing a model. Basically what we're trying to design is an equation essentially that is best trying to take this data and seeing, say we have 100 people and we're trying to, figure out how serum creatinine figures into their GFR, right? You can take that data from the 100 people and figure out a math problem, basically an equation that best fits all that data from the 100 people into this predictive equation. And then I can take that model and then apply it outside to other people. And that can be really handy. That's how we come up with things like, Chad's 2 scores. That's how we come up with things like, Cockcroft-Gault equations. That's how we come up with all this stuff is based off of these models here that help us to predict what's going to happen with our patient that, was not a part of that original study there. Okay. So again, fitting models to data is typically what we're doing from the original, the original research, and then you can simulate data from the models. I can say, okay, well, if I have a patient who is 73, they weigh 100 kilograms, and they have a creatinine of 1.2, I can predict what their GFR is. And if that's a good model, then I should be pretty good at being able to predict that, right? And of course, all of it is determined by how good your model is based off of the variables that went into it, how good the initial data was that fit into it, and all of that, okay? So anyway, so when we're trying to fit a model to the data, we want to figure out like what's the best model that we can design here. This is where we use our multiple regressions, right? So we're using the regression to fit a model to the data, and I'll show you what this kind of looks like. And so I kind of like this idea of models as sort of being like the shoes and the data are the feet, right? You can find shoes that are like custom tailored just to that one person. Maybe you went to a really nice cobbler and they've designed this model that perfectly fits your foot. But then if I try to take that shoe and fit it on anyone else, it might not fit that well, right? And so the question is like, well, how tightly does that model fit the data? Or how tightly does that shoe fit the feet? And then how good is that model if I try to take it and apply it to anyone else? So there's going to be a little bit of give and take there. No model will be perfect, and it's only as good as the data was first based off of, okay? The regression does not fit data to a model. Rather, the model is fit to the data, okay? So let's compare different models together. So this is a major part of some of the biostatistics here that we're going to see. So models with more parameters, models with more parameters always fit the sample data better, but may not reflect what's actually going on in the population there, right? So you can come up with a million different variables. Oh, thank you, Sydney. That's actually not mine. It was from, I don't know where I got that from, but I think it's a pretty good one. So anyway, so they don't actually reflect. So you can use like a gazillion different variables there. But again, you know, if you think about trying to figure out someone's creatinine clearance, like I don't have a whole lot of data. I have their weight, I have their age, and I can pretty reasonably get their serum creatinine. But obviously we know more things go into that, right? And so we can get as many variables as you want, but it may not be super practical. So that's what's really tough. So a model with too few parameters won't fit the sample data very well. As we'll see, you won't get a very tight fit to that. And then a model with too many parameters will fit the sample data really well, but the confidence intervals are actually gonna be really wide, right? And again, if the confidence intervals are really wide, that's not gonna be super predictive, or it won't be really handy. It won't be useful if I try to then apply that to my patient who I'm seeing in the ER or getting called on in the middle of the night for tox consults or something like that, right? So when you're doing comparison of models, again, your null hypothesis is always going to be that there's no predictability here between X and Y. And so in that case there, the slope of that line is always going to be 0. And you're saying, okay, well, here's my null hypothesis that the slope here is 0. Looking at the data, you can probably tell that that's not going to be true, that you're probably going to be able to reject that null hypothesis. And when you determine what your best fit line is based off of this, you can then come up with a 95% confidence interval that says, okay, well, if I actually applied this data and this best fit line back into GenPop, right? So your general population that you're concerned with, you know, where would this line actually fall? And recall, it could shift, right? It may not be this line perfectly, but it could shift there. As long as this 95% confidence interval does not include 0, right? Does not include the null hypothesis, then you can be fairly certain that you can reject that null hypothesis, and then you find that, yeah, there is a statistically significant relationship between X in their predictions of Y, okay? So as I mentioned, that R squared is just telling me what percentage of Y I'm able to predict from X in the data that you have there. So what you're gonna find is less variability of points around that value here. So the tighter this fits onto the line, the less likely you are to keep that null hypothesis and the more likely you are to reject it. So the more variability there is here, the wider these confidence intervals are going to be. And again, if that slope includes 0, then it's not going to be able to be rejected. And you say, okay, well, I can't say that there's any actual relationship here. Okay, let's get into our multiple and then logistic regression. I think this is the more interesting thing in terms of, you know, some of the data that you're going to see out there, some of the research you might look at, and like real world application of some of this stuff. And so there's a good example of like a study we'll look at here. So, and again, in a laboratory experiment, you control all of the variables, right? So we can see that if I change one variable in the data, I can then measure what changes and then analyze that using standard statistic tests there, right? So these are like the original research articles you're going to be seeing when you're developing some of these models here. And again, you can look at, or at least in these types of experiments, you can analyze how one variable is influenced by several variables, right? So we can look at one variable y, which is going to be our dependent variable, and we can look to see what a variety of independent variables, how that's going to affect that. And that's really going to be handy when we're doing called our multivariable variable or multivariate regression. What you're going to see here in some of these kinds of experiments and in most observational studies, the outcome you measure may be affected by multiple variables. We mentioned that how blood pressure is affected by a lot of different things than just a medication. It can be affected by time of day. It can be affected by gender, ethnicity, all kinds of stuff, right? So what we can use here is these multiple variable methods, a really handy way, and you're going to see these are pretty widely used. And so we're just going to be talking about sort of the basics, okay? So as I mentioned, multiple regression methods are used for a lot of purposes. So they can impact, or they can look at the impact of one variable while adjusting for others. So I can adjust for things like patient's gender. I can adjust for their age. I can adjust for any number of different things there. And then I'm trying to create a model, trying to create an equation to make useful predictions. That's where things really get interesting, is when we can make a model and then apply that out to other patients, right? And so then also we want to understand scientifically how various variables might impact an outcome. So if I change something like, for instance, if I look at differences in exposure to asbestos or something, and I'm looking at an outcome of Y being mesothelioma or something like that, you can look to see what sort of impacts those changes in the variables will have an impact on that outcome, okay? There's a lot of different types of multiple regressions that we're going to see here, all of which kind of fall under this umbrella of multiple. In terms of variables, the models all predict an outcome, which is that dependent variable Y. So the dependent variable is always going to be Y. There's only going to be one of those. But then when we're looking at our predictors, our independent variables, that's going to be X. And you can have as many of these as you want, right? It can be one or it can be infinite. But there's always going to be one dependent variable when we're doing these type of regressions here. When you hear multivariate, it's something you may hear using consistently. I'll probably do it as well. It can refer to a couple different things. So for instance here, sometimes referring to methods that are comparing several outcomes at once, which is technically the correct way to use it. That's not what we're really going to be focusing on. What we're more looking at are multivariable, which makes sense because we're using multiple X's in order to try to predict Y there, okay? So this is more of what we're going to be focusing on today when we're looking at one outcome and then several independent variables. So multiple linear regression. So this is the one I think is the good example here. So we're finding a linear equation that best predicts Y from multiple independent variables. Now again, ultimately linear regressions are fairly simple, and it's probably going to be as complex as we need to get for our purposes here. Certainly if you were to take more classes on this, you would get much more in depth, and certainly out of my depth. But this is kind of good enough for us in terms of like reviewing the literature and whatnot, is what you'll see most commonly. So our example, right? Does lead account for decreased kidney function with age? Okay, this is a study, a little bit older study, but I think it gives you a good idea of kind of what's going on here. So if you're just looking at the title of this, what would you think your your dependent variable is going to be? Well, does lead account for decreased kidney function with age? Well, I'm going to say that my dependent variable here is going to be kidney function, right? So this is probably going to be on the y-axis. And then I'm going to see multiple variables here that are going to be having an impact on that. So one, looking at lead, so lead content in the patient, and then looking at age, right? And so for those of you not familiar with like lead poisoning and things like that, obviously people who are, living in older cities, for instance, they may have more like lead-based paint in the home, kind of water contamination, a lot of places for lead to sort of pop up there, right? So they're investigating this relationship between lead exposure and kidney function, but they also know that there are other things that go into kidney function than just a person's lead content, or at least that's what they're predicting. And so you can see that kidney function decreases with age. And so what's interesting with these multilinear regressions is that you can control for some of these other variables just to see what impact that another one has. So I can control for the effect of age with the data you're looking at and just tease out what effect the lead is having, okay? This will make more sense here in just a moment, but this will be handy because it is going to be, you want to try to tease out how each one of these independent variables is affecting the entire model to see, what percentage of that variability is really accounted for with just that one independent variable, right? On your dependent, which in this case is going to be kidney function. So what we're trying to see is, okay, we want to know whether accumulation of lead could explain some of the decrease in kidney function seen along with aging, okay? Because again, we know it's going to go down with age anyway. We want to see if lead is contributing, okay? So they had 965 men here. We're only going to look at the male data because that's the example from the book that I was using had here. And so they were measuring serum lead and they were measuring creatinine clearance, okay? What they found was that subjects with more lead tended to have a lower creatinine clearance. Not going to be a useful finding, as we know that, as lead increases with age and creatinine clearance, we just know that that's kind of a natural thing there. But we want to figure out what sort of contribution that this lead is having, independent of the age of the patients there. Because in this case here, age is confounding the investigation between creatinine clearance and lead specifically. So I want to try to control for the patient's age and see what contribution lead is having in that case here. So confounder, this is an important term you want to focus in on, is any sort of extraneous variable that correlates either positively or negatively with the dependent and independent variables. This is something you want to try to account for when looking at your data, because it could be introducing bias and could be skewing your data one way or another, right? So you want to control for things like age, but maybe you want to control for things like whether or not they have diabetes. Maybe you want to control for things like whether they have a history of, dialysis or something like that. Could obviously be affecting your information there. So we use multiple regressions to try to adjust for any confounders. And again, you could have a near infinite number of confounders, but you're going to find that the more you do that, the more chances you're going to run into some multiple comparisons problems, as we'll see here in just a little bit. But what we're going to see is that the x variable, our independent that we're really concerned about, is going to be the log of lead concentration. This is, again, an independent variable, because this is what we're setting as the thing we want to look at. And then the y variable, or dependent, is going to be the creatinine clearance. That'll be on the y-axis there. As I mentioned, the model is predicting its value from a baseline value plus the effects of 5 independent variables. So we wanted to look at 5 different confounders that could be affecting this, and we're going to see what effect that it has on that creatinine clearance. So here's the ones that they were looking at. They were looking at log of the serum lead concentration. Doesn't really matter if you know why they're using log or not. Just know that they're looking at serum lead concentration, looking at the age of the patient, looking at the body mass of the patient, because we know that can have an effect on creatinine clearance. Looking at the log of their GGT. This one's not going to be quite as important. As also focus on whether or not they're using diuretics. Maybe that has a role to play as well. And so then ultimately they're looking at all these different variables. These are ones they thought that were important to account for, and how all of this will then come into factor in and ultimately produce our creatinine clearance. And so what's interesting here is that I can, by doing something like this, and I can look at all these different variables and put it into the data. By looking at the graphs, I can control for these different things and just tease out the effects of age alone. I can tease out the effects of body mass by itself, or, as this researchers were really curious about, the lead specifically. Okay. So here you can see the different variables. Again, some of these are going to be, plus or minus. Some of these are binomial sort of variables. So like diuretics, like they either never took a diuretic or they had a diuretic, right? Some of them are going to be in various units. Like you can use any of these, and it's perfectly fine when you're developing these sort of graphs, as we'll see in just a moment. So our goals here, so the multiple regression fits the model to the data that they actually are collecting there, to find the values for the coefficients and make the model come as close as possible to predicting the actual data, right? So they're determining what math equation is going to best fit a line that's going to fit all of that data that they're collecting there, right? So there's a best fit value for each of those parameters along with a confidence interval. This is going to be important because we can look at those confidence intervals and tell whether or not that variable is having any statistically significant effect on the actual outcome, the dependent variable. And so you're going to see a p-value gets reported for each of those independent variables. I'll show you what that looks like here in just a moment. Recall, though, that our null hypothesis is always going to be that the parameter, each individual parameter, is going to have a slope that is basically 0, or just a flat line there, such that it has no predictive capabilities of trying to figure out what the dependent variable is going to be, or creatinine clearance in this case here. Okay, so basically it does not tell us any specific information about how y is changing. So when you're doing these multiple linear regressions, again, they don't really distinguish between the x variables you really care about and any other x variables that you're adjusting for. In these cases here, you have to be able to distinguish which ones you're trying to look at as terms of like what your main focus is, and then adjusting for the covariates. So that way you can say, okay, well, taking out of the picture the effects of age and diuretic use and all those other things, what is the effect that lead has specifically? So when you hear me say things like this is being controlled for age, I'm basically taking the variability in the data due to age out of the equation, right? I'm taking it out of the out of any kind of sort of influence on the dependent that I'm actually caring about versus the independent that I'm investigating specifically, right? And so This will make more sense when you look at the graphs too. So their goal was trying to answer, after adjusting for effects of other variables, which is like age, body mass, diuretic use, is there a substantial linear relationship between the log of the lead concentration and creatinine clearance? So they're controlling for all those other variables I mentioned, those other 4 independent variables, and seeing what is the relationship here between lead concentration and creatinine clearance. Okay, what they found was there's a best fit line for lead, and it was minus 9.5 mLs per minute, basically meaning that as lead concentrations went up by 1 unit, they found that creatinine clearance dropped by 9.5 mLs per minute. Again, the graph will make more sense in a second here. And when they adjusted for other variables, they found that an increase in lead, as I mentioned, was same with a decrease in creatinine clearance of 9.5. So taking the effect of things like age, body mass, diuretic use, taking that out of the running there and controlling for that, they found that lead specifically had this sort of impact here. And they got a confidence interval. It was negative 13.9 to 5.1. And recall that our null hypothesis here would be that if lead increased, that it would have 0 effect on creatinine clearance. Because this does not include 0, they could reject the null hypothesis. And they would see that if you actually apply that to the general population of men, like they were studying in this particular data here, that if you increase lead concentrations by 1 unit, that they would have somewhere between a drop in creatinine clearance between 13.9 and 5.1. Okay. So, and what they found was basically a 10-fold lead increase in concentration would reduce renal function by about 10%. You can see here ranging from about 1 to 20% based on the data they found. So this is what it would look like here. Basically, if you looked at the lead concentration on the x-axis, because again, this is our independent variable, and then the y here being our dependent or creatinine clearance, you can see this linear regression as that lead concentration goes up on the x-axis. We see that there's a decrease in creatinine clearance. And because these confidence intervals does not include a slope of 0, that's why we were able to reject that null hypothesis. Okay. And what's cool is you can actually look at the data, and then by controlling for lead concentrations, you can then also look at what effect did age have, what effect did body mass have, etc. And you can get actual p-values for each one of those. Okay. And again, you're going to say here that your p-value needs to be less than 0.05, but because I can interpret those confidence intervals and determine whether it's statistically significant or not just based off of that, I don't even have to look at a p-value. I don't even need it, right? And that's what's kind of cool, is because a lot of people who are sort of fledgling researchers and looking at journal articles and stuff like that, they're always like really invested in that p-value. Like, oh, I gotta have the p-value. I gotta know whether it's less than 0.05. You don't even really need that, right? If you can understand and interpret confidence intervals, you're going to be golden, right? So that's a really important thing that I like to instill in my students, because I want them to be kind of a one-up on other students, because they can interpret this stuff with a more clear head, with a more sort of context than others. So when they were doing that, when they actually looked at the model and fitting it to the data, they found that there was an R-square value equal 0.27 for lead. So the sound was, or I'm sorry, with the model they came up with, basically only 27% of the variability in creatinine clearance was explained by that particular model. Everything else was either other variables that they were not accounting for, or just random variability. So if you were to look at this and look at this model, this would not be super great. Like, you wouldn't want to use a model on your patient to try to figure out their creatinine clearance and it only being able to explain 27%. Like, you want to account for the other 73% as well. So, and again, here when they're looking at it, there's too many independent variables to really come up with like a best fit line. So this is not perfect for something like that. That's why if you're looking at something like Cockcroft-Gault, it's taking into account 3 factors, right? Or 4 factors, I guess, male versus female, age, weight of the patient, and then their same creatinine. So again, too many independent variables, the confidence intervals get too wide, and it doesn't really make sense to apply it to your population, because again, the R-square is not going to explain enough of the variability there for it to be really clinically important. And here's what the actual data would look like. So you can see here how the data looks kind of looks a little bit messy, just because there's so many data points, right? There's almost 1,000 data points here for this particular study. But notice here that the confidence intervals, the data is so clustered around this line that it seemed to be very unlikely for you to actually get a slope of just 0 here. So you can definitely reject that null hypothesis and say, okay, my p-value is 0.0001. It's pretty good. But again, there's not a whole lot of the variability can be explained by this particular line. It's only 27%. So the bigger this is, the closer this is to 1, the closer it is to 100% of the variability of y is being explained by x. And so you want this to be a bigger number, closer to 1 if possible. Okay, so as I mentioned, correlation does not imply causation here, right? So when you're doing sort of an observational study, like just looking and collecting data on someone's creatinine clearance and their lead concentrations and age and stuff like that, that's observational, right? The researchers didn't actually do anything. And so it doesn't actually prove cause and effect, right? Your best bet would actually be giving a random sample of people, say take 100 people, give 50 of them varying levels of lead, and then the other people no lead, and then seeing how their creatinine clearance change, right? Obviously, a lot of these studies are not super ethical, and that's why a lot of them do not get performed. That's why like tox data is always like notoriously bad, because I can't intentionally overdose people on drugs and then try out different treatment, modalities and see what works best for them. Because again, it's not really ethical to do that. I can't have a bunch of people and purposely bite them with snakes and then see how good one drug works versus another. So again, if you can do more direct interventional sort of research, the stronger the data is actually going to be when you're doing these sorts of things. So that, again, the best way to overcome any doubts about cause and effect is actual direct experimentation, where you actually have an intervention that researchers are going to perform here, right? So another thing we could do potentially is logistic regression. So this is going to be used when there's two possible outcomes. So instead of just having one y value there could be more than one. So this is an example here. They were looking at a study. They're trying to predict the prevalence of obesity in Iranian women. So it's kind of an interesting specific take on something. So they were looking at their outcome here. So it was obesity, right? They're considering that to be a binary, either yes or no, and they were basically creating a model to predict that prevalence of obesity as a function of various demographic variables. Okay, so what do they want to do? They want to look at 3 independent variables here. They want to look at age and number of years of education. Those are continuous, right? So age is obviously a continuous variable. How many years of education is continuous? Smoking status, marital status, and the place of residence, which can be a binary sort of thing. So I think they're looking at whether like rural or more city-like living locations, or marital status, married or not, smoking status, yes or no. So those are all binary. And then looking at economic index, and it said 4 categories here. And so I basically assigned 4 binary variables. You could use this as like an ordinal variable as well, depending on how they want to do that. So anyway, so at the end of 14,000 Iranian women, which, if you think about population or study population and the number of people you're including in your study, like, if you had a value of 14,000, that's really good. That's a lot of people you're including there. It's going to give you pretty good data, which is easier if you're just doing things like, epidemiologic research, where you're just getting a lot of demographic data that might be easily accessible through, normal data collection, things like the census or something like that. Anyway, so they're using logarithms here. They get odds ratios, and they're looking to see, basically using logarithms because it kind of helps to make things look symmetrical. Don't worry about this point too much. It's kind of a more esoteric point there. But basically what they can do is they get odds ratio for each of these independent variables to see what sort of effect that those are going to have on the outcome there of obesity here, right? And so this odds ratio is answering the question specifically in one particular x value. It was increased by 1, so an independent value, by controlling for all the others, so controlling for smoking status and economic status and things like that, how much would the odds ratio be expected to increase in terms of the odds of someone being obese or not, okay? So again, when you're looking at odds ratio, if a ratio is 1, that means that the independent variable has little impact on the outcome, right? Because 10 divided by 10, if there's no difference between the two outcomes, then that's 1, right? So if a ratio is 1, or if the confidence interval includes 1, then you're going to be able to say, okay, well, I can't really reject a null hypothesis. I don't know whether this independent variable actually has an effect on the outcome or not, right? At least with the data that you have. If it's much higher than 1, that means it's increasing the odds that if someone is positive for that variable, that they are going to have a higher odds of being obese. And if it's less than 1, then it would appear like that it would be actually protective, and meaning your odds of being obese are lessened if you have that variable, right? And so we can see here that it's kind of interesting how some things can be protective against obesity and other things might be increasing your odds, right? just based off the data they have here. So again, whether they're living in an urban setting, yes or no. Age, again, looking at that as a continuous variable, education, smoking, all of that, right? So here are the values, and again, they don't have to give you a p-value. We can determine whether or not it's going to be statistically significant just by looking at the confidence intervals, because we know we're doing an odds ratio. So if it includes 1, if it encompasses 1, then that way we can say, okay, we cannot reject the null hypothesis. I cannot say this is statistically significant. If it does not include 1, then I can say, okay, I'm rejecting the null hypothesis. This does have an effect here on changing the odds ratio. It's statistically significant. The p-value is going to be less than 0.05 just by virtue of the confidence intervals here. So what are some things that look like it was increasing our odds ratios of being, or increasing the odds of being obese? Well, things like living in an urban setting, right? Perhaps they're not walking around as much, or maybe they have access to better transportation, or who knows what the case is, right? This doesn't really look into why this is. It just looks at the associations here, the correlations. So an odds ratio, so it went from 1.915 to 2.2369. That's fairly narrow. So you can say, yeah, there's like a 2 times increase in odds of someone being obese if they live in an urban setting, if they are an Iranian woman, right? So again, pretty specific, right? Could this be directly, could you extrapolate this to women living in the US? Maybe, maybe not. I don't know. What are the differences between Iranian women versus US women? Could you extrapolate this to men? Maybe, maybe not, right? So those are things you can kind of ask yourself when you're looking at the research to see, okay, well, does this apply to my patient? And how different is the study participants and the people I'm dealing with? Let's look at something like age. So age had an odds ratio of 1.02, and you can see here it does not include 1. So it is statistically significant, but if you were to look at the clinical significance here, you'd say, well, this is only like a 2% increase in the odds of someone being obese. That's like nothing, right? So that's almost no difference there versus something like living in an urban setting. It's twice as much, right? So this would be much more clinically important, I think, for our purposes than something that was just 1.02 in terms of odds ratio, but still statistically significant. So a lot of things are statistically significant, but don't really mean a hill of beans from a clinical standing here, right? Let's see if there's anything that is going to be, actually, these are all just the ones that are statistically significant here. Notice here some of these are actually protective against being obese. So for instance, like smoking, the odds are 35% lower basically if someone's a smoker for being obese here. And again, you can see, a little bit more wide-ranging confidence interval there. So again, there could be some variability to it, but it appears that, yeah, this is statistically significant. This seems to be that people who are smoking are less likely to be obese. And some of that does make sense because, typically smokers are going to be a little thinner. Smoking has an appetite suppressant sort of effect and some other factors that go into that. So all these things to make a difference, right? Of course, the degree of difference is all total in the odds ratios there. And so again, that's the other thing too, when you're looking at these, this is controlling for all of these other factors here. So this is the smoking, when you're looking at this is smoking alone, because you're controlling for whether or not they live in an urban setting. You're controlling for their age. You're taking all those other factors out of the equation and just looking at smoking specifically. And again, the benefit of that is that you can look at an individual variable to see what effect it's having on your dependent variable, your outcome, okay? So again, looking at this, you can see that, for example, when the subject lives in the city, the corresponding odds ratio is 2.13. So that means their odds are twice as high of being obese as someone who is living in a non-urban sort of setting there, right? And again, we're keeping all the other independent variables identical, okay? Again, 95% confidence interval range between 1.9 and 2.4 because it does not include 1. We obviously know that the p-value is less than 0.05 because it's an odds ratio. It does not include 1, so we can reject that null hypothesis, right? Okay, so just a quick wrap up here in terms of Q&A. Do the X and Y values have to have the same units to perform a linear regression? No, they can be totally different units there. There's no specific relationship between units between independent and dependent variables there. They can be different, and oftentimes are. Can linear regression work when all X values are the same or when all Y values are the same? No, there needs to be some variability in the data. That's the whole point of it. If Y never changed or X never changed, then I can't really use either one as a predictive value there. And so, or if Y is all the same, then there's really nothing to predict. Y just doesn't change. So that really wouldn't make sense. Will the regression line be the same if you exchange X and Y? So this is important too, because again, when you're doing a regression, you're predicting y from x. So you don't want to mix those two up. But if you swap the definitions x and y, then the regression line is going to be different unless the data points were just happen to be lining up perfectly there, so that every one of those was on that line and the r value was 1, which is unlikely to occur. So yes, you don't want to be mixing those up. You got to know which your independent variable is. That's going to be on the x-axis, and then the dependent is going to be on the y. Right. Do you always have to decide which variable is the outcome dependent and predictors independent at the time of data collection? You don't have to necessarily. In some cases, it may not be distinct until you start to kind of analyze the data a little bit. You want to be cautious though, because you don't want to necessarily do what they call like overfitting the data, because then it's not going to be super useful when you try to apply it to outside of your data set there. Again, the shoe gets to be too tightly fit around that foot in order for it to be applicable to really to anyone else. So be cautious with that. But usually someone's going in with sort of an a priori idea of what they want to compare, and so that will already be decided beforehand. It doesn't have to be though necessarily. Does it make sense to compare the value of one best fit parameter with another? Not really. You know, the units of each parameter tend to be different there, so we can't really directly compare those. And again, we're not going to really get into anything more advanced than that, so that's kind of good enough for our purposes there. And then do all the independent variables have to be expressed in the same units? Nope, we saw before, like in that lead example, they all can be completely different. Okay, so that's the end of this section. Let's go ahead and go into chapter or PowerPoint 8 here. Just want to see if there's any questions on the sticky board. Nope, I assume you guys are just getting this stuff like this is like review for you guys. Like, this is easy. Why is he even talking about this stuff anymore? All right, so this is called the rest of statistics, which means everything else we haven't covered yet. It's all here, right? It's all here. No. Okay, so getting into it. So let's talk about some things here, some other types of tests we're going to run into. If you recall, we talked about the t-test before. Remember, the t-test was helpful when we were trying to compare the means of two different groups together to see if they are the differences between those means are just due to random chance, or whether they were actually different enough, or the differences that we see, are they unlikely to be due to chance alone, right? Because yeah, there is a statistically significant difference here between these means, right? So for instance, if I have someone on a blood pressure medication, one group in a blood pressure medication, the other on placebo, and look at the changes in blood pressure between the two groups, can I say that the changes there are due to chance alone, or are they so different that it's very unlikely, less than 5% chance, that this is just due to random variability, right? Now I want to get into something that's a little more complicated. It's called the analysis of variance, or ANOVA. So this is kind of like a fancier version of a t-test that helps to determine, instead of just using the means of two groups, we can then use as many groups as we want, basically. So ANOVA just stands for analysis of variance, and it's just a means of being able to compare multiple groups together at the same time to determine if there is any difference amongst the groups, okay? So its use is a little more specialized. We'll look at some examples of this in just a moment here. But again, ANOVA provides a statistical test of whether or not the means of several groups are all equal. It doesn't tell us where the differences lie, it just tells us, is there a difference anywhere, or roughly all the groups equal, and any changes between groups is just due to random variability there. And again, t-test is going to be when you're doing it between just two groups. If you're doing more than two, then you're going to get into ANOVA, right? And again, these are still tests where we're assuming there's a Gaussian distribution to the data, that we're assuming the data is normally distributed. So these are still what we call parametric tests. We'll get into some examples of non-parametric examples later on. So, and again, why do we do ANOVA? Why not just do like multiple t-tests between the different groups until I find out where the differences lie? The problem with that is that it increases your chance of a type 1 error. If you recall with the multiple comparisons problem, the more you can make different comparisons just sort of willy-nilly, the more your chances are of finding a type 1 error, unless you control for that sort of thing, right? We talked about the Bonferroni correction and things like that. ANOVA is a really nice, quick way to look at all the groups at the same time to see, okay, is there a difference somewhere here? And then once you say that yes, there is, then you can dig down further and can use individual t-tests to find out where those differences lie. Okay, so we'll look at what that really looks like when we have an example here in a moment. So let's do an example here. So one way ANOVA comparing the means of 3 more groups. And again, we're sampling these from a Gaussian population. That's the assumption here. So there's a study here. They're interested in hormonal changes in female runners, right? So basically, they're measuring luteinizing hormone in non-runners, recreational runners, and then elite runners, right? And so what their definitions are may vary from study to study, which may make comparison between studies difficult. But they can set their definition if they're doing this one research article here. Maybe it's more than a certain number of miles in a week or something like that can be making the differences here. And so what they could do is they could lump the females into these 3 different groups based off of their running history, and then look at the hormone levels, right? And then see, okay, well, is there a difference here between any of these groups? Okay. And again, oftentimes the researcher's not going to publish all the raw data. They're going to show you more of a summary of the data they're actually finding there, along with whatever statistical test they're finding there. And again, we're not saying that LH levels can be useful to predict if someone's a runner. I can't run an LH test on a female patient and say, it looks like you're an elite runner. You run about 50 miles a week or something. I don't know actually what elite levels would be, but you run this many miles a week. That would be ridiculous. That's not what we're saying here. We're just looking to see, like, is there a difference in the amount of luteinizing hormone these females are expressing, and how that may correlate with their running status. Okay. And so what we can find, though, is that the mean differences, though, could be distinctly different between, say, non-runners to runners. And we can look at that based off of the graphs we're going to see here in a moment. So just to orient you to this a little bit. So here you can see the non-runners, recreational, and then elite runners. Again, this is defined by how they set up their definitions. The log of the luteinizing hormone. You can see here, that's the mean values between all 3 of these. And then standard deviation, standard error of the mean, you can see their n value. Again, you want to be focusing more so on the actual mean values itself, the n they're including in here, because that can have an effect. What do you notice about this? Had about 90 or so in the non-runners versus recreational runners, only 30, about 28 in the elite runners, right? Why do you think that is? Probably because there's fewer people that meet that definition of an elite runner versus people who are considered to be recreational versus non-runners. Could that have an effect on the data? Perhaps, right? Maybe you'll see more variability. Who can say, right? But let's look at the graphs here. So you can see how the different runners are going to be graphed here. And then you have the log of their luteinizing hormone, and you can see here we have that standard deviation plotted along with the mean value, and then also the standard error of the mean. If you recall, just a little point here to mention, remember standard error of the mean is influenced heavily by the number of people in the observations, so n. So remember, as n goes up, your standard error of the mean typically goes down, and that actually bears out here. If you were to look at these 2 groups, non-runners and recreational runners are pretty similar, versus you see here there's a big increase to the elite runners in the standard error of the mean, and their sample size was a lot smaller. So that does sort of bear out there a little bit. Okay. So what we could do potentially is I could just run a series of unpaired t-tests, right? Again, unpaired just means that there's no relationship between any of the data points. No one would fit simultaneously in the non-runner and in the elite runner category, so they're all separate from one another. So it would be considered an unpaired t-test, assuming no one's related to one another. And I could go ahead and run a series of different t-tests. I could say, okay, let me compare non-runners versus recreational. Let me compare recreational versus elite. Let me compare elite versus non-runners. But every time I do one of those t-tests, I have a 5% chance of finding an erroneous result, right? Of rejecting the null hypothesis. The more times I run that, the chances of making type 1 error keep going up. Okay, so unless I correct for that, I'm going to run into that problem. I'm more likely to make a type 1 error. You can control for that, but then it's going to be so conservative, you'd find that the p-values you'd have to hit are going to be so small that it's very likely, or the chances go up that you're going to make a type 2 error. So how do I get around that? Well, I can basically run an ANOVA just to see, are there any differences at baseline? And if there's not, then I'm done. I can move on from the study there. If I do find something, though, then I can start to dig down a little bit further, and that's where I can talk about multiple comparisons and all of that. Okay, so basically when you're running an ANOVA here, if the null was true, and there's no difference between the 3 groups, then there would be a 5% chance that each t-test would yield a significant p-value, right? That's just saying that, at a baseline, 5% chance, less than 0.05, you're going to find something significant. And again, with 3 more comparisons, that chance of any one of those is going to go up much higher than 5%. So type 1 error rates just get too high when you're doing all these multiple comparisons, with each one using a p-value of 0.05. So, as I mentioned, the one-way ANOVA compares all the groups at the same time. In the calculated one-way ANOVA, the p-value was 0.0039. So definitely less than 0.05. So what does this tell us? Well, it tells us that there's a difference between some of these groups here. There may be multiple differences, statistically significant differences between the different groups, but there's at least one somewhere, okay? In this case, our null hypothesis would be that the mean concentration of luteinizing hormone is the same amongst all three populations, that there's no differences between there, and any differences we do see are just due to random chance. But because we have a p-value less than 0.05, we can reject that and say, no, there probably is an actual difference here between luteinizing hormone expression in these runners here. Now that I know that there's a difference somewhere, now I gotta find it. Okay, so now I can then go on and do some more research and do some more individual tests. If this had been greater than 0.05, then I would not have been able to reject that null hypothesis. I would be done. I couldn't do any more tests there because, again, the ANOVA told me there's no differences amongst groups. So based on, when we're looking at assumptions of the ANOVA, it's the same as the unpaired t-test. Everything has to be randomly selected. All the groups have to be independent from one another, and we're assuming that we're pulling out of a Gaussian distribution. It'd be nice if the standard deviation was identical in all the groups, but oftentimes it may be slightly different amongst one another. But that's some of the assumptions. Again, really large standard deviations mean there's a lot of variability, which means there might be more outliers, which could be affecting whether or not you truly have a Gaussian distribution or not. So, we can also see that there is a difference between just a normal ANOVA and then what we call a repeated measures ANOVA. And so this is going to be the same difference between an unpaired and a paired t-test. That being when you have groups that are related to one another, like say for instance, I had someone who did a diet. So they had a group of people and they all tried a keto diet for 90 days and then they had a washout period and then they tried an all carnivore diet for 90 days. And then I looked at the pre and post because those samples are related to one another because it's the same people doing different interventions. I would be using a paired t-test in that sort of case there, right? With the repeated measures ANOVA, this is the same thing as a paired t-test, meaning that the groups have some relationship to one another. So if you hear a one-way ANOVA, that means it's independent samples. If it's a repeated measures ANOVA, that means there are related samples here. Okay. So measurements either are made repeatedly on the same subject. Maybe they have undergo, like say, 3 different diets, for instance. Maybe they do, Atkins and they do keto and then they do something else, right? That could be one way you could see that there, but it's the same people doing different interventions. Either that or they're recruited like a match set, or maybe they have like some relationship to one another, maybe family or otherwise. Or if you're doing like a laboratory experiment, if you're running the same sample multiple times, something like that, right? So other ways we can do this. So other measures of ANOVA, aside from just the one way we're looking at, here we can find that we can actually do what we call a two-way ANOVA, and that's going to be if we were looking at multiple different categories here. So when I'm saying that, like if we were to then take the runners and then break them out based on age groups as well, we could use something like a two-way ANOVA to help us out with that. So let me show you an example of that. So a two-way ANOVA kind of gives us testing 3 null hypotheses and gives us 3 basic p-values here. So again, getting a little bit more fancy. So what it's telling us is an interaction between age and luteinizing hormone, because we know age could have an effect on hormone expression, right? The null hypothesis here would be that there's no interaction between the 2 factors. And then it looks at the first factor being going to be luteinizing hormone amongst the different exercise levels. And then the second factor would be looking at age and its effect there on luteinizing hormone levels. So it's interesting because now you're using 2 independent variables, not just whether they're runners or not, but now you're using age as well. And so that using a two-way ANOVA can be really helpful to look to see if there's interaction there, whether the first factor matters, so exercise status, and then second factor being age, seeing that if that has a role to play. So again, you can find examples of that. Two-way ANOVAs are going to be less common you're going to run into, but frequently you'll see a lot of like one-way ANOVAs done in the literature. So you'll certainly see that quite frequently. So let's say we have an ANOVA that does show something. Let's say it gives us a p-value less than 0.05. Well, what are we going to do in terms of multiple comparison tests afterwards? Because like I said, once you have a p-value less than 0.05 in ANOVA, then I got to do some further digging to see where the differences lie between the groups there, okay? So as I mentioned, you get a single p-value from a one-way ANOVA. And again, if it's greater than 0.05, it means all the groups are identical. Any differences I see are just due to random chance. But if I do find something, p-value is less than 0.05, I'm going to do multiple comparisons tests. And just like I said, multiple comparisons can be problematic because the more I do, the more likely I am to find a type 1 error, assuming I don't make any changes to my level of significance, my alpha, right? And so again, that's where you can do some corrections here, so that way your chances of having a type 1 error are mitigated and are kept reasonable. So, as I mentioned here, they were looking at the luteinizing hormones for those 3 groups of women based on the running status there. We found that one-way ANOVAs gave us a pretty small p-value, showing that there's some differences there between groups. And so now I need to dig deeper, as I mentioned. So, what we're saying here, though, is that when we're looking at a family of comparisons, so now that I have to dig deeper and look between recreational to non-runners, non-runners to elite, and elite to recreational, now I'm looking at a family-wise error rate, and I'm going to set that to be 0.05. So instead of saying each test has to be 0.05, I'm now saying my 0.05 is going to apply to all these tests, and I'm going to have to divvy it up, right? Like taking one pie and then cutting an equal piece for each one of those. Yeah, you don't get the whole pie, but also your chances of overeating and making a type 1 error are going to go down, okay? Problem though is it's decreasing power to detect real differences. So again, anytime you're decreasing your chances for a type 1 error, you're going to be increasing your chances for a type 2 error. And frequently you'd rather be making a type 2 error and not rejecting the null hypothesis than making a type 1 error, right? You don't want to say, look at this great discovery I made, and it not be true, right? So here the goal is to compare every mean with every other. And so here's an example of one you can do. It's called a 2-keys test. And this is a means of doing repeated measures after a positive ANOVA, or ANOVA that shows a small p-value here. And so you can see we get the results of confidence intervals and conclusions about their statistical significance. And again, by doing the 2-keys test, it has now changed what my level of significance is going to be. It changes the alpha such that it's more difficult for each of those comparisons to become statistically significant, but again, it reduces that type 1 error rate as well. And so next, we're going to show you the 95% confidence interval between the mean of each group against each other. And so again, that multiple comparison of confidence intervals applies to the entire family. So each of those comparisons I make only gets a portion of that 0.05 when they're going into this, okay? All right, so actually looking at this, we can see, okay, the difference in log of the luteinizing hormone, because again, you're just taking the differences between the means of the groups. So, recreational LH level minus the elite, non-runners minus the elite, all that. And then I can go ahead and do that. Since we know the ANOVA is positive, we can go ahead and do the 2-keys test, and then we get our confidence intervals. Notice here they're fairly wide, and that's pretty reasonable. Anytime your type 1 error rate, you're trying to reduce that, the confidence intervals tend to increase as it happens. So what we can see here is that if there's no difference between the groups, then the value would be 0, right? Because, again, 1 minus 1 is 0. So there's no difference between the groups, and it would include 0. If the confidence interval encompasses 0 here, because we're doing a mean difference, then it's not going to be statistically significant, okay? So if these confidence intervals include 0 here, because we're doing a difference between groups, not a ratio, then it's not statistically significant. So what you can see here is that when you compared then the recreational versus the elite runners, there was a non-statistically significant difference there in their means of luteinizing hormone, which makes sense too. Even the value itself, the mean difference is pretty close to 0. When comparing non-runners versus elite runners, this was not statistically significant because it encompasses 0. However, the biggest differences you did see that was statistically significant, though, was the non-runners versus recreational. Okay, so going from a non-runner to a recreational runner had the biggest impact on the mean difference here in luteinizing hormone. Now, again, what is the clinical impact of this? I don't know. I don't work with, this population specifically, but maybe there is some sort of impact. Someone at least did the research study, so someone is at least interested in it. Maybe this is clinically important in some cases, or maybe this has some effect on, in terms of ovulation rates and elite athletes and things like that, So there could be some impacts here, but you yourself as a clinician have to determine whether it's significant to you or not, right, from a clinical standpoint. But statistically, this was the only comparison that actually was statistically significantly different, okay, because it did not encompass 0 there. Okay, and again, that 2-keys test, that was a 2-keys multiple comparison test that allowed us to have a family-wise error rate of 0.05, meaning that we were able to control for that multiple comparisons problem and make our type 1 error rate lower, right? Even though the type 2 error rate. Now, had I just gone and done the comparison between recreational and elite and used a p-value of 0.05, could I have found a statistically significant difference there? Perhaps. The confidence intervals probably would have narrowed up, but you know, who's to say? But you can't really do it that way. That's not really good science to just run multiple comparisons until you find something that works there. So this is the right way to do things, right? Okay. And so again, the 5% significance level applies to the entire set, the entire family. So that's what we call family-wise error rate. And so again, it just gets divvied up. So in that case, there was 3 different comparisons. That 0.05 is then divvied up amongst the 3 comparisons. So 0.05 divided by 3, whatever that is. And so again, it's more difficult for each of those comparisons to achieve significance, but it also means our type 1 error rate is going to be kept manageable. Okay, so we're looking at the logic of multiple comparisons here. So again, with more groups, the confidence intervals between means become wider there. So just with 3 groups we had between non-runners, recreational, and elite runners, there's 3 possible pairwise comparisons. So again, the p-value, you know, is only divided by 3, that 0.05 divided by 3. You know, so still reasonable, but let's say I had 5 groups. Then I would have to do 10 different independent comparisons. So now, instead of achieving an alpha of 0.05 to achieve significance, I'd have to go 0.005. Again, more difficult to do unless there's a really large differences between the different means you're comparing there. Also means that confidence intervals are going to be wider, so it's more likely that they're going to include 0 and be non-significant. Okay. So, again, you're going to use a multiple comparisons test. They're going to use data from all the groups, even when comparing 2. So in this case here, the one-way ANOVA is based on the assumption that all the data are sampled from populations with the same standard deviation, even if the means differ. So meaning that the variability amongst all the different groups should be relatively similar. Because we're going with these assumptions that we're using normally distributed data and all of that, it does give our comparisons more power, right? So when using parametric tests like t-tests and ANOVAs, where you're going under the assumption you have normally distributed data, they have more power to detect differences. Okay, we'll look at some cases where that's going to be violated. We have to switch over to using non-parametric tests. That'll be important to look at later on. But again, just to give you an idea of the number of pairwise comparisons, the number of groups, the number of as you go up to, you know, say a number of 20 different groups, you know, you could do that. You could look at 20 different groups and all compare them, but notice how many different actual individual comparisons you're having to make there, right? So if you just did, you know, kept your alpha at 0.05 and saying every one of these 190 comparisons has to be less than 0.05 to be significant, you're guaranteed you're going to find a lot of significant stuff. Doesn't mean it's right though, right? Because again, your type 1 error is just extremely high there. It's probably getting close to 100%. However, by comparing for this also and doing that 2-keys test, it makes it much more difficult for each one of these. So the more groups you have, the more difficult you are, more difficult time you're going to have to actually find statistically significant differences here. So just keep that in mind. Okay, so like I mentioned, t-tests, ANOVAs, all of that, that's undergoing the assumption that we are using normally distributed data here. That's what we call parametric tests when you're using normally distributed data. If you are violating that assumption, or you're not sure if your data is normally distributed, typically what we're going to do instead is what we call non-parametric test, right? Where we don't make any assumption about the population distribution, right? Or if you say do a test for normality on your data and it fails, or if you have a bunch of outliers that are skewing the data, that violates that assumption of a Gaussian distribution, in which case here we have to reject that assumption and switch over to using non-parametric tests. And so if you recall, one of the things we ran into when looking at means, if you recall, means or averages are highly susceptible to outliers, right? So you could have someone, you know, maybe the class average for a test is like, you know, so you have like one of those undergrad chemistry classes and with like 300 people, and some with weeder classes, your freshman semester of college, and you know the class average for a test is like 65, but you have that one person who made 100 and it skews the whole thing, screws the whole thing up. That's an outlier, right? That's not normally distributed data typically. And so what you're going to run into is if you can reject that, instead just rank everything, right? And so just rank everything in terms of this is the lowest value, so it's 1. Then you have the second lowest values, third, fourth, and all the way up to your highest value. By ranking everything in order, and instead of a mean, now you're using the median value, the middle value, that removes or severely mitigates the effect of outliers, okay? Because even if I have a huge outlier, it doesn't matter by how much, it's only going to move my median by 1 point, right? By one rank. And that's handy, right? So by mitigating the effects of outliers and using non-parametric tests, we're able to basically make more sound statistical comparisons. That's really the important thing there. So again, like I'm saying here, most commonly work by ignoring the actual data values and just ranking them. So the lowest value is the first rank, and the highest value is that last rank, and then the median is that middle rank there. And so, as I mentioned, unpaired t-tests, ANOVAs, they're all assuming a Gaussian distribution, so they're all going to be parametric tests there. Here, we're not making any assumptions, okay? So for instance, when I did my data for my research study in fellowship, right, I was doing it based off of coral snake bites. You know, there's certain people who are much more likely to be bitten by coral snakes than others. So for instance, you know, male patients and children, much more likely. That I knew my data was not going to be normally distributed. It just wasn't likely. So instead of worrying about whether that data is normally distributed, I went ahead and just said, okay, well, I'm just going to reject that assumption and use non-parametric tests. Okay, you'll see that a lot in the literature. They'll just go ahead and use non-parametric tests because they know their data is not going to be normally distributed. It's hard to do that. You have to have a really true random sampling, and that's really tough to do in medical literature. So anyway, so as I mentioned, non-parametric tests make no assumptions about this. Simple non-parametric tests rank values from low to high and then analyze the rank. So the actual values don't matter. You're just looking at the ranks. And it's kind of tough for us to think about because we're so like detail, you know, data or driven, and so it's a little bit more of an abstract way to think about it, but fortunately you're still going to get the same number sort of reported out. You know, it's just that the underlying math that goes into it is different. Okay, so you're not going to have to actually calculate this stuff out, but just know that we're using different tests and we're using the ranking of values, not the values themselves, in order to calculate these things. Okay, so again, it ensures the test won't be affected by outliers and doesn't assume any particular distribution. So the benefit of doing this, actually the downside of it, one, is more difficult to achieve statistical significance. These are more conservative calculation, means more difficult to achieve significance. Okay, so that's a bad thing. So you're more likely to make a type 2 error. The plus side, though, is that these stats are very robust, right? Because it means that they are unlikely to be violating any assumptions, meaning that if I then apply this out, if I do find something that's statistically significant, I'm pretty sure that that is true, that it's not a type 1 error. I can then apply that outside of the sample and apply it to the population, and I should still get the same results. So it's more difficult to achieve significance, but when you do achieve it, you can be very confident in those results, okay? So always a bit of a trade-off between these different things here. So looking at this, so comparing two unpaired groups. This is first off called the Mann-Whitney test, or if you're seeing it, Mann-Whitney U test. These are more difficult to associate in your mind because typically it's named after the person who discovered it, the statistician who developed it. So again, I apologize for that. I don't name these things, but I still have trouble sometimes and I have to look it up. But be familiar with some of these common ones you're going to run into. They get pretty wild in terms of their naming, as you'll see when we look up some of the literature. But the Mann-Whitney is a non-parametric test comparing two unpaired groups and getting a p-value. So this is like an unpaired t-test, but using non-parametric data, using non-normally distributed data, just using the rankings of the data and not the actual values themselves. Okay, and so there's steps you can read to go into that, but again, the main point here is that they're using the ranks, they're not using mean values. You're not worried about outliers so much here because again, we're not really worried about that in terms of sort of the effects that this is going to have. That you're not making any of those assumptions like you would for an unpaired t-test, right? So anyway, I'm gonna make sure I'm not going to go over time, but I got sometimes switch gear if I'm starting like at 12:30 or 2:30, switching gears in terms of what time I'm stopping. So I got to remember I have till 9:40. But anyway, so when you're making assumptions here, some samples are randomly sampled and are independent, but no assumption about the distribution, right? So these are much more robust results we're going to get here. Less likely to make a type 1 error than we would be if you're using a parametric test, like an unpaired t-test here, right? And you're still going to get a p-value, right? You're still going to be able to interpret this just like you would if it was a parametric test. It's just the underlying math has changed, okay? And again, you're not doing the underlying math because you're not a statistician. You're going to be a PA. So here if we were looking at that effect of the norepinephrine on the rat bladders here, you can compare the two. Again, if we don't want to make any assumptions about the distribution here in terms of the effects of the rats, and you just want to compare the old versus the young, just go ahead and use the rank values here and do the Mann-Whitney U test, and you're going to get roughly the same results as an unpaired t-test. It's just these are going to be more conservative, and so are more difficult to achieve significance. It's harder to get a p-value of less than 0.05 in these cases here. Okay, so let's say we want to compare two paired groups. So instead of using a paired t-test, we're going to use two paired groups here, but we're not going to assume that there's a normal distribution to the data here. So this is where we get a Wilcoxon matched pairs signed rank test. Again, I apologize for the names of these. I wish I had come up with them because I would have named them something much easier to remember. But a Wilcoxon's test is, again, comparing two groups. And again, the null is that there's no difference, right? So again, you can think about these in terms of analogs of one another. Paired t-test versus a Wilcoxon matched pairs signed rank test. They're doing the same thing. It's just a matter of what assumptions they're making in terms of how the math goes into it, okay? Again, I'm not going to get super into the steps on how we're going to do each of these because, again, I want you to think about them as parallels in your mind. Again, know what the parametric variety of tests is, an unpaired t-test, a paired t-test, and know what the non-parametric counterpart is going to be. Because, again, you'd be using them in roughly the same ways, just a matter of the underlying data. If you assume there's a normal distribution or not. If not, then you're going to go with the non-parametric test. If there is, then you use a parametric test. That's kind of the detail that I want you to get out of this. But again, if it's a paired group, make sure you're using a paired test and not using an independent test, because again, that will violate that assumption, and then you can have a higher chance of making a type 1 error, okay? So again, a Gaussian population, the problem with using a non-parametric test is that with, and again, you can even break it up into small versus large samples, you're going to have less power to find differences. That's kind of the problem with non-parametric tests is you have less power to find differences. So type 2 error rate goes up, type 1 is relatively low, okay? With large samples, it doesn't really matter quite so much. You're going to get nearly the same results here because with large samples, you have much more power, and so you're less likely for this to have an impact here. The bigger problem, though, is if you're dealing with non-Gaussian populations, and you use a parametric test for that, this can be really problematic because you're going to be more likely to find a type 1 error. You're more likely to reject a null hypothesis when you should not have. And so because of that, you're going to potentially be making false claims about your data that are not true. Okay. Again, with using larger sample sizes, the effects of this gets mitigated, but you're going to find in a lot of medical literature that we don't have large sample sizes, right? So especially depending on the or I guess like the specialty that you're in. So for instance, like with tox stuff, I don't have a lot of huge sample size populations, but with cardiology, you can find that. So again, keep an eye on the data. If they're using parametric tests, make sure that they do some sort of test for normality, because it's going to helpfully tell you whether or not you're dealing with the Gaussian distribution or not. Okay. All right. So some other points to get into. Let's talk about sample size here. As I mentioned, many experiments, clinical trials are run with too few subjects, right? And remember, if you have too few people, you may not have the power to actually show a difference there, between your groups. But this is a problem in a lot of studies because it's hard to recruit people for things. Sometimes it's an issue of ethical concerns of mitigate or sort of limiting the sample you have access to. Sometimes it's an issue of convenience. For instance, we were running a study at the hospital I was doing my fellowship at years ago, where we were comparing a new antivenom to the gold standard antivenom. And so the problem is that we could only take patients, enter them into the study while someone that worked on the study was actually there and present. And unfortunately, ERs are open 24/7. So if someone came in with a snake bite at 3 a.m. on a Saturday, because they had too much to drink, and they said, "Hey, look at this," then that person could not be entered into the study because no one was there that was working, right? That worked on the study. And so again, you can find there's lots of challenges that go into actually recruiting enough people to be in your study there. And so an underpowered study is oftentimes going to be not all that too fruitful because your type 2 error rate is going to be too high, right? You're unlikely to reject a null hypothesis. Even if a real difference is there, your study just wasn't powered to find it. And you're going to find that in a frequent critique of a lot of articles, is that they'll say, hey, we had a small sample size, we're likely underpowered to find a difference here. Had we run this with more people, perhaps we would have found something, right? So that's a common sort of out that a lot of researchers will have when they're looking at their data. If they don't find anything, if they're publishing negative results, then they can say, well, we weren't powered to actually find it, okay? And again, they can go into a study doing a power calculation to tell them how many people they should be recruiting. They should do that, and then compare that to how many people they actually did recruit, okay? And again, even if treatment substantially changed outcome, there's a small chance of finding it if you have an underpowered study. So this is a common problem you're going to see out there in a lot of medical literature. So what can we do here? So we can do an ad hoc sort of thing where we just collect and analyze some data, and if the confidence intervals are not narrow as you like, or maybe if the results aren't statistically significant, you just keep collecting more data and then you keep reanalyzing until you find something. This is not great. All right, you don't want to do this because it's basically just keeping torturing the data until you find something, until it tells you what you want to hear. And that's not good science. We don't want to do that. You could do conventional methods though. So this is where you choose a sample size based off power calculation, right? We talked about that before. Basically, you're going to determine what your the effect size you're looking for is, how big of a difference you're looking for between the groups, and then what your alpha level is and your power level and all of that, which are usually pretty standard variables there. And then it tells you how many people you need to recruit to find a difference this large. And sometimes you need 1,000 people, sometimes you only need 100 people to find the differences there, but it tells you basically how many you need. At that point there, you don't really need to do any adjustments. You just analyze it based off the data you collect there. Now, in some cases, though, you may actually find adaptive trials. And so this is where you can do what they call interim analyses, where you start a study and you're running it for a while, and then you, at certain points, will go ahead and analyze the data that you have already collected. And then you can have an idea of whether you need to maybe make an extension to get more data. Sometimes you need to cut studies short, actually, in some cases there. So this is more done in large clinical trials where there's a lot more money being thrown around. You have multiple sites that are being involved, and usually this is determined sort of a priori, right? So you already have an idea of where the interim analyses are going to be run here. We actually had one just recently, within the past couple of years at Nemours. We were doing a study on a drug for spinal muscular atrophy. That was a lot of kind of a big area of research for some of our neurologists there at Nemours. And there was a study where they were comparing placebo versus active drug for this disease state. And again, if you ever want to see a really sad disease state, it's spinal muscular atrophy. Very, very sad outcome for a lot of those kids. They started a study where they did placebo versus this new experimental drug, and they stopped it early because the results were so good with the active drug that it was not ethical to withhold that from the other participants. They found such big differences in outcomes in terms of survivability and symptomatology, all of that. They said, we got to shut this down early. So again, sometimes you'll find that the results are so overwhelmingly positive that you may shorten a study. That's not common, but it can happen with like large clinical trials and things like that, right? So remember, sample size has a huge impact on confidence intervals, right? So confidence intervals, as sample size goes down, confidence intervals are going to get wider, okay? As your sample size gets larger and gets more approximate to the actual population, that you're interested in, then it's going to become very, very narrow. But again, that's a challenge, get more people involved. So it's hard to do research, hard to recruit people, hard to keep people in the study. And so that's why oftentimes studies come in underpowered in a lot of cases here. And again, by determining how big of a confidence interval you want to have in the first place, you can actually calculate how many people you need to recruit in order to get that. So again, study, sample size is difficult for a lot of those research articles out there. So anyway, let's see. So we have one more session here before we do our review. I'm trying to think, how big is... Yeah, this one's 47 slides. I'm not going to have enough time to talk about that. So would you guys be totally upset if I stop this early? Let me know your thoughts on that. I'm going to see if there's any questions on the sticky board here. I'm sure most of you are probably asleep at your keyboards anyway. Again, I'm a wonderful cure for insomnia. If you ever have some trouble sleeping, feel free to listen to me. No, I'm sure most people are screaming at their computers. No, stop. Yeah, it's fine. So we'll go ahead and next time we meet, we'll go over the last PowerPoint, which would be number 9. And then the following meeting, we'll have our first journal club. For this one, it's going to be mainly us kind of going back and forth. So I'll give you the article early. I want you to review that. And then we can go ahead and kind of talk through how I dissect an article and sort of determine how... things I find that are important, things that I look for, and then that way with the following journal clubs you'll have a better means of kind of doing your own sort of reviews and dissections and whatnot. So that'll be group-based study. We'll see you there later on. So hang on for that. Then we'll do our review and then we'll be good to go. So thank you all for joining me. If you have any questions in the meantime, either post them up here on the board or you can email me. Again, thanks for hanging out with me. Almost had half the class here for this wonderful subject. Hopefully made it a little bit interesting, but it is what it is. So thanks a lot. I'll see you guys next time. Yeah, have a great rest of your day as well. I think we'll go ahead and cut off the stream here. So you guys have a good one. I'll see y'all later.